Hey, who's all here? Good to start off the week. Oh my gosh, it's Monday. A little chill music to start us off right here. Hair just keeps getting longer and longer. Maybe get a cut. You never know. Cut for spring break, right? That's the way it goes. Good stuff right here. Checking out all the chats. TE stuff. Nice. Might have some 320 swing by. Hey, who's in the chat right there? Marcus, it looks like. Hey, what's up, Marcus? Good to see you here, Jack. What are you guys wondering about? So I'm going to start a little talk on 320. BS 320 regression advice. Let's go check it out. So come on and feel free to ask questions right now. Hey, Sloan, it's your birthday. Happy birthday, Sloan, right there. About p-values? Oh, I could talk about some p-values right now, Jack. So I'll show some here in a second. That was kind of my plan. So let me get some p-values going right here. And then we can talk about what they mean, and I can relate this to 320 if you can say which class you're in if you like. But watch this. You ready? So what I'm going to do is I'm going to make a linear regression, which we're covering in 201 and we're covering in 320. So it's kind of a neat crossover right now. So we're going to store into M a linear model that explains weight of a car with the horsepower of a car. Let's actually do horsepower as the Y variable of interest. Hey, Simone, good to see you here. Ask the questions if you got them. We're going to use weight to explain it from the data empty cars. This is already loaded in. And there's the model. And let's visualize the model right here. And that's a horrible visualization, but we'll get it better in a second. So what generally happens is cars weigh more. Horsepower is generally water for cars. When you do regression tests, yeah, this is exactly what I'm going to show right here, Jack. So let's actually take a look at that. That's exactly where I'm going. So you and me just mind melding right there. So right here, how would you explain the relationship in this data? How would you explain the relationship in this data? Like, what's going on right here? Cars that weigh more, generally what? How would you explain the relationship in this data? Cars that weigh more, generally what? Cars that weigh more, generally what? We can look at the summary of it and find out the slope of the line. So we can see the slope right here is 46.16. I would say two cars that differ by weight in 1 ton are expected to differ by 46.16 in their horsepower, where the car that weighs more is expected to have a higher horsepower. So generally speaking, cars that weigh more generally have higher horsepower. It doesn't mean they will. Like, you could look at that car right there. That car has the highest horsepower, but it's not the heaviest car. It's a bit of a outlier, right? It's far away from the trend in the data. So with this right here, we got to throw 100 points for happy birthday, Sloan, right there. When you look at the 3 regression tests, and this is where I wanted to start. People can cover this in their midterm if they want for my class. There are 3 tests. Can you name the 3 tests, Jack? And so, Sloan, this kind of, in 201, you might know the 3 tests we're about to do. If you had to check conditions for this regression, which is what we're going to do right here, so this relates to 201, what might you check about this regression? And you might have a saying you're thinking of, and that relates to what Jack's asking about right here. So what would you think about? What would you do? Spread, yes, equal spread. Yes. So I thought shape center spread for a second. I was like, well, yeah, kind of. But you're saying equal spread, right? Which is we want homoscedasticity. Can you explain nested if statements? Oh, we could take a look at those, yeah. And so you want QQ straight enough, no outliers, plot doesn't thicken. Does that make sense, Jack? QQ means 2 quantitative variables. Straight enough means the line goes through the data well, no outliers, and plot doesn't thicken. Now, there's one more we really didn't mention, which is normality of residuals. And so let's go here to check regression. What do you think check regression does for us? Check regression is going to what? But for the correction form, oh yeah, I need to do those probably tonight, Sloan. Sorry about the delay in that. I will need to do those tonight. Weekend was a little bit busy getting everything prepared for the midterm. I think I told everyone to have them submitted by Sunday night. So I'm going to go through and go do those. So you should see those corrections come in. But that's on my list. No worries. Thank you for saying that. 100 points right there. Good reminder. But yeah, I wanted everyone to do them so I don't do them piecemeal. I don't do them one day and come back to them. It's easier to sit down and be like, I'm going to correct exams. What do you think check regression does for us? Like, what is the point of a check regression? Just think about what it's going to do. It's going to check the regression to see if there's issues. So check regression, checks your regression to see if there's issues. So the only one we fail is where. The only condition we fail is where. And so this is a review of tool 1 right here. If you look at the conditions, the null hypothesis is linearity is good. So when a p-value is high, is that reject the null or fail to reject the null? What do we do when a p-value is high? Reject the null or fail to reject? And you saw right there, Jack, you are right. This is the only one where there's an issue because the null hypothesis is normality is good, and Marcus has it right there. You reject the null. Great job, Marcus. So the null hypothesis is normality is good. And then if you look over here, you can see if it's high, just let it fly. You know, Jack, right there. You know the sayings. So this one is where you reject the null that normality is good. You can literally speak of the null hypothesis for each of these being linearity is good, equal spread is good, and normality is good. All of these pass, and the p-value for 1x is the same as the p-value for the overall model right there. But normality, if you look, should you look at plot 1, 2, or 3 for normality? Plot 1, 2, or 3 for normality. The first, the second, or the third. Which plot should we look at for the normality of the residuals? Which is this test. So you can kind of look at this one. I don't suggest looking at it. That's a decent answer there, Marcus. Good job. I wouldn't look at plot 2. We look at a normal quantile plot, a QQ plot for normality. And we could actually do it by going over here and doing QQ, M residuals, and we'd get the same sort of plot. So this is the plot we're getting right here. And is it good or bad, and why? So is it good or bad, and why? So it's all about, and so want is very subjective. And Marcus sees it right here. Yes, there's huge problems at the end, and these are the high outliers that have observed values much higher than we expect. And if you look at the original regression on this, there are observed values much higher than we expect. It's these values right here, those 1, 2, 3, 4, that have values much higher than we would have expected if normal. So a lot of people say, wait, so is a low p-value good or bad? A low p-value only means what? A low p-value only means what? Like a low p-value only means this all the time. Like if a p-value is low, it means this. Like what could you say every time a p-value is low? What? It's statistically significant. Or you reject the null, which is what we do when it's statistically significant. So let's look at this example right here, where if we do core.test and we do empty cars, $ miles per gallon, comma, empty cars, $ horsepower. Now, the null hypothesis here is there is no correlation. The null hypothesis here is that there is no correlation. The alternative is that the true correlation is not equal to 0, which means there is correlation. So that's like a easier way to say it than null hypothesis is true correlation equal to 0. Alternative hypothesis, true correlation not equal to 0. But so if we reject the null here, we're saying what? We have evidence of what? So the null is, for this test, there's no correlation. So if we reject the null, we're saying what? The null for this test I just ran is there's no correlation between those variables. So rejecting the null would mean we have evidence of what? So you always have to ask, what's the null hypothesis? We have evidence there is correlation, right? So we have strong evidence to suggest there is correlation. So if you want to find correlation, hey, that's a great thing. Now, when we ran our check regression, the null hypothesis here was linearity is good. Now, does it sound like you want to reject that or don't want to reject that? The null hypothesis for linearity is good. Does it sound like you want to reject that? If you want to use your model and you fit a line to it, does it sound like you want to reject that or don't want to reject it? Because the null is linearity is good. Like the linear fit is good. Like I usually try to make it sound easier. Like the line's a good idea is what we are assuming. You don't want to reject that. Do you want to reject that there's equal spread? No, all of these assumptions are good things, like things you want your model to have, equal spread, line, and you don't want the residuals to be non-normal. So the null that the residuals are normal is rejected, and then we have over here the QQ plot, or the normal quantile plot, showing us that there's a big error with these high values, these extreme values up here. So in this instance, like, what do you want? Well, if you want to use your model, you wouldn't want to reject the assumptions that kind of make your model usable. Does that make sense, Jack, right there? Like, sometimes we kind of don't want to reject the null. In this instance, when we're saying we believe assumptions, rejecting the assumptions would be reason to not use our model. So we would probably want, if we're trying to explain a relationship, for there to be a statistically significant relationship. So in this instance, when we test correlation, the correlation has the null hypothesis. There is no correlation, which is kind of the reverse or the other side of the alternative. So does that make sense right there, Jack, right there? This all is, and really good questions on regression, because that's what we're covering in 201. And this is all some QQ straight enough. No outliers. Plot doesn't thicken. Because here's two quantitative variables. There's a straight enough relationship. There are outliers. That's the problem with this regression. We could even check this. See, they're not going to have big influence. We could go to an influence plot. And that high point actually doesn't have undue influence on the plot. And you can see it's deleted studentized residual, which is basically a standardized version of the residual. So we could say, you know, we ran an influence plot to check to see how bad these outliers are. Since they don't have high leverage, they're not actually influencing them all that much. It's a little bit of a concern with this one right here. That's the point that was way above the line. And the reason it's over here is leverage is done from the mean of the x's. So this point right here is near the mean, the center of the x's. And that's why we don't see it having high leverage. The points over here have the most extreme leverage, as do the points over here. So in the influence plot, these points right here, those three below the line, those three below the line right there are these three below the line right here. They're the ones most to the right. Now there's a point above and below, and those points right there above and below are, this point is the point above the line, that point's the point below the line. Although you're looking at the left, leverage of 0 is when you're at the mean of the x's. More on this plot in my class later, but a lot of people don't understand how that plot works. You're basically folding this in half, and if you're at the mean of the x's, you have the least leverage. Things over here, think of it like a seesaw, and if you were to press down over here, it would bend the bar, but if there was a fulcrum right here, something it bends on, pressing here would have very little leverage. So, and deleted studentized residual is the distance you are away from the y, and to be influential, you need both of them. Well, really good stuff right there. Simone asked about nested if statements. Okay, so the biggest thing, and this is kind of a thing on coding, so let's talk about nested if statements for a second. And please ask more questions. We don't have any other questions right now, so it is open questions. Nested if statements. Another question, when someone says fit the model, that just means use the element. Yep, 100%. This is the fitting of the model right here, and then storing it into, so you fit it and then store it. So it's basically create a model. Would you mind explaining what R squared is trying to explain to us? R squared is the percent of variation in y explained by the variation in x. So when we look at a value of R squared, it tells us how much we understand in the y variable of interest using the x variable. So knowing the horsepower of a car gets us about 43.39, or knowing the weight of a car gets us about 43.39% of the way to understanding the horsepower of a car. That's what the R squared means. It's basically how much of the variation we understand. More specifically, and let me move the timestamp on this. More specifically, because we can go a little more detail, can you go over the upcoming 306 project? 306? 320? 306? What's 306? I don't know 306. Important to know this output right here. This is the amount of variation the x variable explains, and this is the amount left in the residuals. So if you were to take both of these values right here, you would have the total variation. So watch this. That's the amount of variation that exists, and this is the amount of variation we explain. And the amount of variation we explain is R squared. So the ANOVA, no worries there, Sam. I was like, 306? The ANOVA actually shows you how much of the variation in the total variation that there was, we explained. Like, this is what we explained. This is what we didn't explain. If you add them up, you have the total variation. And then if you take the top value right there, then you would have the amount we explained over the total that exists. And the original variation right there, you're welcome, oh man, good to see you right here. I passed, nice. Oh man, so good to see you, and really glad about that. We'll keep asking those questions. If you have something the videos don't answer, let us know, and we're glad to have you as a mod right here. And visiting from another class and doing well. We appreciate that. I want to help people out, so got 100 points for the students right there, Amin. This right here is the amount of variation we explain out of the total variation that exists, and that is R squared. And that's the deeper concept, that R squared is the reduction in the error from the naive model. We have the naive model, we have how much we reduce the error by, and that's what we got going on. Hot lamps. Cullen, good to see you here. Hope you're doing well today. Just yeah, good to see you. Sending all the awesomeness from Disney down there. So awesome. Got StatLab or got Discord down there. The last thing, did someone say something else? R squared. Yeah, we did that. Okay, let's do nested ifs. Nested ifs. So when we do nested ifs, if you ever do something nested, you want to do it in parts. Don't write multiple lines of code at one time and expect it to work. So when you do an if, like let's say I'm going to take people and group them into like tall, short, super tall, things like that. I'm going to load up some data right here. And let's get heights. Okay, these are the heights of individuals. And this comes from Reg Class Survey 10, which is a data set inside of Reg Class. So with this right here, we're going to take this vector. And we're going to say right here, if else. Now, if else is one of my favorite ones because it does the if else across a vector. And we're going to say if somebody is greater than or equal to 78 inches, we're going to say super tall. And then right here, we're going to say not super tall. And basically everyone's, oh, there's a person who's super tall right there. That is right? Super is 1P, right? Superman? I think so. He's not Superman. So we have this right here, but here's the thing. Run your code each time. Run your code each time. Every time you create something, run the code. Don't write out a whole bunch of lines of code, expect it to work. If you notice, I write something, I run it. I write something, I run it. And you have to do that when writing code, or else you're going to run into problems where it just doesn't work. Because now I'm going to take this same code I have right here and nest it inside of the false. The way this works is it evaluates this vector and it says, if it meets these conditions, the true's right there, run this code. If it is false, run this code. So for the falses, I'm going to go inside the false and nest this. Now, I can't make it exactly the same. I'm going to say if somebody is greater than or equal to 6 feet, I'm going to say tall, and I'm going to say not either right here. And then I run this, and you notice we're getting it. We should have that super tall individual here somewhere, but we should have at least one super tall. Where's my super tall person? There we go, super tall. So now we've nested it inside, and then we're going to do the same procedure again to the not either, and we're going to go right here. We're going to hit a new line, and then we've nested it again. And you see I deleted something I shouldn't right there. It's because it's wrapping right there. And then we're going to say if they're greater than or equal to 65, we're going to say medium or average, and then we're going to say short. Or let's say, let's just say neither. And then we're on this. Uh-oh. See, now we got a problem. We're missing one right there, I think. There we go. So now we have that. Then we're going to do the same process again of going inside the false right here. Put this right here. And then we go, let's go 58. And below average and short. So you can do the same thing with weights. Just kind of makes sense. And there we go. So now we have this right here. What you could do is you could store this into X. And then you could go here and go a factor of X, and then you have it as a factor variable right there. And yeah, so doing these small steps right here is key. Like do it in steps, do it in parts, and make sure you can walk through your code because now we have a vector we could add on to a data frame, and that's kind of key right there. So yeah, with that, continuing on. Yep, be right back here, everyone. we're back. So the key to coding is just to write it in parts. Do it in small individual parts. Don't try to write the whole thing. Don't try to do multiple parts at once. The smaller amounts of code you do, the better it is. So you do little bits of code, and then, we usually say that right here. Wrong thing.
Little bits.
There we go, little bits. So don't write all your code at once. Do it in little bits, and that's where you succeed with coding. Because I've seen too many people say, I'm going to write all this code, I'm going to get all this done, and then none of it works. So the nested code right here worked out really well because we just worked it little bit by little bit, and then it all worked. Well, what other questions do we have? Let's see right here. Nested if statements. Might need to look at some Pearson. Pearson work. Chill music right here. Chapter 7. Assignment manager. Chapter 7 is due when? It's due on the 10th. Oh, and then my gosh, chapter 8 is due on the 21st? That's so far away. Holy mackerel, what have we done? Chapter 7 quiz just opened up. I hate that we do that. We like to work ahead, and I don't mind. So I kept it the same. Let's take a look right here. Why answer is not matching in... I don't have access to the coding exams. What are you trying to learn right there? I don't have access to the coding practice exam. Definitely reach out to your instructor. What are you trying to learn? Which coding practice exam question are you trying to do? I don't have access to them though, so dun dun dun. Let's see some chapter 7 homework. Let's do it. Okay. Determine if the following statements are true or false and briefly explain why. Choose the linear model that passes through the most data points on the scatter plot. Doesn't sound the best. Okay, false. The linear model usually passes through exactly half of the data points. No. False. All the data points either touch the line. No. The line usually touches. Yeah, it minimizes the sums of squared error. So that's a very technical thing. But when we make linear models, which we were making here previously, we don't choose a model that goes through all the points. The line is trying to reduce the error. It's trying to get closest, basically, it can to all the points. If you notice, the line really doesn't touch all the points. And you do get about half above and about half below. I mean, not perfectly, because you can have a lot of models that really have problems, but you want like an even scatter. So the line is going to reduce the sums of squared error, which we talked about previously is the R squared. The reduction in the sums of squared error is the R squared right here, which can be found via an ANOVA. There's the amount we reduced it by. There's the remaining error. So if you take these values right here and add them, you can find the total error that existed. I go over this a little bit in my class, but it's just a technical thing. And that value right there, which I can show again, that value is R squared. So that is the amount we reduced the total error by. And we don't go that technical into a 1. But that's the goal of this line. And if you reach an R squared of 1, all the points would be on the line because there'd be no more error. So it does reduce the sums of squared error. That is exactly what it does. The residuals are the observed y minus the y predicted values by the linear model. Observed minus predicted, exactly. And I usually like to say actual minus predicted. So that is very true. I don't see anything false about that. Yep. Residual is the actual minus predicted. I prefer to call this actual and call that predicted. And that's a very important thing to know. Least squares means the square of the largest residual is as small as it could possibly be. No, no, no. Least squares, and this is what we're talking about. And somebody here, I'll take a look here in a second. I see a question. We love questions. Least squares is not about just this one point. So when you talk about the residual, it's how far the point is above or below the line, and the square of that is a sum of, or a squared error, and then you'd find it for all of them. So when we talk about the least squares line, it's that the line is going to minimize this error. And that's what the first thing was talking about. The line reduces the sums of the squared error from the naive model, which is a bigger topic. but it's going to get as close as it can. And the reason we square the residuals is because if you just sum the residuals, they sum up to 0. That's a good thing to know sometimes on the test, because some are above, some are below, and they would just average to the line. So instead of just summing the residuals, we sum the squares of the residuals. Now, residuals are basically errors because they're how far they are away. So when you think of sum of squared residuals, well, it's the sum of the squared errors. So we call it SSE for short. So these represent a squared error. And if you add up all the squares, you get the sum of the squared errors. And that is, for this model, this value right here is the sum of the squared errors. This is the reduction, and this is what total existed when we began. So the reduction is the amount explained, which is the R squared. If you understand that, you're ready for upper level classes. So that is the technical aspects. So this is very false. Least squares means that the sum of the squares of all the residuals are minimized. Yeah, it tries to get as close as it can to all the points. So good technical stuff right there. Write one line of code that returns the GPA of the tallest student in the sample. Afterwards, write a response regarding the person's height and GPA. So if you were to write a line of code, what function do you have that can find the tallest student? There's quite a few functions, but what functions would you use to find the tallest student? So someone here will answer that next, but what functions would you use to find the tallest student? Answer true or false, briefly explain why. Some of the residuals from a least squares linear model will be positive. We could use max. We got to use some combos there. So that would find the height of the tallest person. Marcus, good answers right there. Some of the residuals from a least squares linear model will be positive and some will be negative. Yeah, I mean, that's generally true. The false statements, there's just, I love my Pearson, but there's ways to, like, the falses don't give you an answer that I could give that would be like, watch this. We'll do X is 1 to 5, Y is 1 to 5, and then we will make a model right here with Y explained by X, and then we'll look at the model. It's going to be a perfect line, and all the residuals now you should see are equal to 0. It's residuals. So all the residual, well, let's round them. Let's go to here, options. I don't know why it's doing that to me. It should be 0. Options 7. Oh, in the SciPen. That's interesting. What? Look at that. I have no idea. It must be carrying some calculations. Good to see your Emma in the background. Here, let's go right here. And yeah, that's interesting. We'll go round on this. We'll go round to 2 digits, and they're all 0. They should be, because that's a perfect fit. It's a perfect fit, which means the R squared is 1, and it even tells us it is a perfect fit. So that means all the residuals are 0. Everything's been explained from the total variation. If you go back to the idea of the ANOVA we mentioned, we've explained all 10 sums of squared error from the total, which was 10. So they're going for a statement right here, which is true. Some of the residuals from a relation will be positive, some will be negative. Yeah, that's generally true. It's just a weird instance. It's not exactly half the residuals will be positive and half will be negative. No, some will be positive, some will be negative. And if we look at a kind of crazier model, let's do X raised to the, there we go, let's try that. And do we not, oh, I didn't make the model. And if you look, 3 are negative, 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 positive, positive, and there's 5, so it can't be exactly half. And here's the residuals of positive 2, negative 1, negative 2, negative 1, and positive 2. So those are the residuals right there. And yeah, so it can't be, even with 5, you can't have exactly half. And the line tries to go through the middle of the data, so it can't be exactly half. In a least squares regression model line, all the residuals will be equal to 0. No, it's only if it's a perfect model. All the residuals will be positive. No, they unless the weird instance, they're all 0. But barring weird instances, yeah. And so don't try to memorize these. Try to understand what is a residual. When you see the 2 right here, that means this point is 2 above the line. When you see the negative 1 right here, that means this point is negative 1 below the line. Like that distance of the line and the point is 1 below the line. So if we knew the observation of this, the observation of it is, let's go find out. The observation is 16. So it's 16. So the predicted right there would be 17. Think if the observation of y, so the value of y at that point is 16, and it's 1 below the line, well, then the line has to be at 17. And we could easily do that by going here to predict and make predictions, and there's the prediction. So we could actually take actual minus predicted, and there's the residuals. And once again, we can just easily get this by asking for the residuals, but the actual value of y minus the predicted is the residual, and kind of seeing these relationships right here, like, well, if that's 16 and it's 1 below the line, because that's what the residual means, it's the distance the point is above or below the line, well, that has to be 17. Likewise, this point right here is at 11, so it's at 11, and it's 2 below the line, that would make its prediction 13. And there, oh no, its prediction is 11, and it's 2 below the line, so it's 9. Yeah, 3 squared. Haha, that's 9. So 9 is 2 below the prediction of 11. And just working through and solving little problems like this and understanding how residuals work is the key. Residuals is how far a point is above or below the line, which is really what they're trying to communicate right here. Choose the correct answer below. What does the last one say? When you write y hat, which is a predicted value, to denote the predicted value, and y to denote... Oh, we write y hat to denote the predicted value and y to denote the observed. Yeah, that's totally true. That's... Wait, what? Wait, what? Oh! I was looking at the wrong one. Which one did I just answer? Okay, well, I might need to rewind the video and see what did I answer. Did I just not do B? Did I not do B? So some of the residuals will be positive and some will be negative. That is true. Least squares means that some of the squares of the residuals, that means that some, oh, that some of, no. Least squares means the sum of the squares of the residuals is minimized. That's true right there. Yeah, I think I must have not clicked the answer. Yeah, and that you need to know this notation. Y hat is the predicted. Yeah, that was D. Yep. I think previously, I think I answered the question and then I just didn't put the answer and I thought I was on to the next one. So if you review the tape, we talked about how that works and then I must have not clicked an answer. No, but good thing about the homework, we can just redo it. Okay, we have a least squares regression line given right here. So what you want to do is you want to be able to write out the notation on this. Write out the notation underneath this. So can anyone write out the notation? Let's see. Who can write out the notation? This is where you want to be with this, being able to write out the notation below it. So what do we have notation-wise right here? What is value 1, value 2, value 3, and value 4 in notation? Notation is key to your understanding of what's going on right here. Let's see if anyone can get any one of these. So then we need to know, like, oh, well, this is the this, this is the this, this is the this, this is the this. This is the key to your understanding to where you could find these values and find them in output. Very, very important. What do we have? Give it a moment right here and see what people say. Okay. The first one is y hat, which is the predicted. The next one is b0, which is the intercept. The intercept is negative. Next, we have the slope coefficient, which is b1. And then last but not least, we have the x variable, which is length. So this is a model predicting. Yeah, great job right there, Marcus. You got it. 100 points. Great job. Good practice. Yeah. So we have here the intercept, the slope coefficient, and the predicted y value. So we are predicting weight using length. We have the negative intercept, and then we have the slope coefficient right there. Very important to know. What was his residual? Well, now they're asking me to make a prediction right here. A newborn baby was 48 centimeters. So that's the value of X and weighed 39 kilograms. Here we go. So it really comes down to notation with a lot of these. Like the vast majority of problems in this chapter are knowing your notation. So a newborn baby was 48 centimeters long. And then weighed 3 kilograms. So that's the Y value. And so now we have to solve for the predicted. So let's go here and put in 48 times 0.197 and then subtract 5.55. So Y hat. Is that it? 5.1. There it is. So the actual minus the predicted, residual equals actual minus predicted. And so the baby actually weighed 3 pounds, but it had much higher predicted weight. So when you think about this right here, if we had a model, it actually weighed about 3 pounds. This is 3, but the prediction from the line, which would be up here, would be about 3.6516. So is this residual positive or negative? So the baby actually weighs 3 kilograms. And it was predicted to weigh that. So is this a positive or negative residual? It's definitely negative. Great job, Marcus, right there. So it's definitely negative because it's below the line. And then you can just subtract. It's going to be negative 0.6516. So 3 minus, and there it is right there. Really good question. Just knowing how to find residuals and solve for them. Really good because it's a multi-part question where you have to know the notation and then solve for it. What does this say about him? Well, then we just said the newborn baby weighed more than the weight predicted. No, less than the weight predicted. So he weighs, is it he? I don't know. 3 decibels. Yeah. And we want to write this out and visualize this right here to show that the line makes the prediction. So this is the Y hat right here specifically. And so the predicted weight of the baby was 3.6516. The baby actually weighs 3 kilograms. And so the baby is negative 6.516 below the line. And you can see that right here. So the value of the residual, which is this, is right here. And specifically in notation, we always write E equals, and then it would be the actual minus the predicted. So the residual equals to the actual minus the predicted. If the correlation between 2 variables is positive, the slope of the linear model would be positive. Very true. So the way this works is when we do correlation, correlation basically shows us the direction of the relationship. And so I would know here, well, I could have done the correlation of this. So core.test on MT cars. And we have the, I think it goes X variable first. So horsepower, that's a different relationship. Sure, core test, X comma Y. And the correlation here is very positive. And so I would know since the correlation indicates the direction, the slope is also the direction. So that would be indication of a positive slope. Disk drives problem right here. Disk drives have been getting larger. Their capacity is now given in terabytes. So 1 terabyte is 1,000 gigabytes or 1 trillion bytes. A survey of prices for external disk drives from the data shown this data below. Let's predict the price from the capacity. So when we say we want to predict price, price is the Y variable of interest. And that's huge to this problem. That's very key. Capacity is going to explain price. So that's going to be very important. You get a lot of extra information right here, the summary statistics, which are the mean of the X variable, the mean of the Y variable. That little bar means mean of that variable. So mean of X variable, mean of Y variable, the variation in the X variable, the variation in the Y variable. And if you notice, the standard deviation is rather large compared to the mean, which means a very skewed data set. So it is right skewed for both of these. The R right here is the correlation, and they do look to be positively correlated. So what we need to do is we need to open up JUMP. So let's get JUMP open up here. JUMP is going to be a huge help for solving these problems. So I would highly suggest using JUMP. You will see JUMP output on the test. So knowing how to read it is going to be important. We're getting JUMP opened up. And once you get JUMP opened up, you want to go to File, New, Data Table. File, New, Data Table. And that's up at the top. And if you're on a Mac, it'll be at the top of the screen up here. So you can be anywhere inside JUMP and go to File, New, Data Table. It's also Control N or Command N on a Mac. And I can't show it to you right there. Control N is a quick key. So you can just hit Control N and you get a new one, or Command N on a Mac. Little quick thing right there to help out. But now we're going to go here, go to Copy to Clipboard. Copy it. Now we're going to hit Control C or Command C, Control C on a PC, Command C on a Mac. Now that we've copied it, we're going to go back to JUMP, and this is where you have to be careful. Inside of JUMP, you have to go to Edit, Paste with Column Names. Now, make sure you copied it. Make sure you paste with column names, because you'll see the column names at the top. If you don't paste with column names, this won't work. Reason is it thinks that you have categorical data because the name went into the first column, and it should be quantitative, which is the blue over here. You can't simply change it really easily because there's a word here and it won't let you do that. So just open up a new data table and paste with column names. Once again, go to the edit and paste with column names to do that. And there's a quick key for it that I use sometimes. So make sure it's blue. If it's not blue, start over. You're able to, yeah, you could. Great answers, Marcus, right there. Another way of doing it. Yep. So now we're going to make a model to understand price, and we're going to go to Analyze Fit Y by X. So let's do Analyze Fit Y by X right here. With Analyze Fit Y by X, we are going to understand the price with capacity as the X variable. Capacity of a hard drive is going to explain the price of a hard drive. So let's go ahead and click OK right here. Ooh, that's a little nonlinear. It's got this bend. If you notice, the line is kind of there-ish, and it kind of bends. So let's go ahead, go to the red arrow, and go to Fit Line. So we're going to fit the linear model to this data, and you can really kind of see the non-linearity of it. So this is going to be interesting. Even though the R squared is really high, I see some non-linearity, especially those points 1, 2, 3 below, 1, 2, 3, 4, 5 below or above, and then below. That's a bit of a issue. I don't know if they get it. I think they don't get into that. What is the slope of the model? Well, the slope of the model can be found in two spots. We have right here the equation that y hat equals b0 plus b1, and b1 is the slope. And then you should also know that the slope's right there, and it's a positive slope. But the slope's also down here where it's the estimate of the x variable's coefficient. So there's the estimate of the intercept above it, and there's the estimate of the slope, and the slope is statistically significant, which is the statistical significance of the model. So it says to 2 decimal places. There we go. Boom. What does the slope mean in context? It's for each additional, let's see right here, it's for each additional terabyte. We expect the price of a hard drive to be this much more expensive, because you can see right here, it's for additional terabytes, the increase in expected price of hard drive. So it indicates that, what is that? Random text message. Oh. Whoa. Oh, I think I know what this is. Oh man, craziness. What does the slope mean in context? It means that for each additional capacity in gigabytes, the additional capacity in gigabytes for each additional, the way they phrase this, it indicates the price for a hard drive. No, that's the intercept. It indicates the additional capacity. No. It indicates the additional price in dollars for each terabyte. Nice job, Marcus, right there. Again, the right answer before I did. Great work. Just the way they phrase it is not how we would write it on a test. So I always suggest writing it out that for each additional increase in terabyte, we expect the price of a hard drive to be $142.27 more. Know how to write it out because we want you to be able to interpret these for the test. And so I can't state that enough, that make sure to write these out and interpret them in your own words. The intercept is the one that I talked about, a hard drive with no capacity right there. And make sure to grab that negative. It does go down here and you can see where it hits. It is negative. So don't forget the negative. And there we go right there. Boom. And it indicates the price for our hard drive with no capacity. And this is because it's when X is equal to 0, we expect Y to equal B0. Using our interpretation, we would say when capacity is equal to 0, we expect price of a hard drive to be negative 298. This is not logical because you can't have a hard drive with 0 terabytes. It would have no space. And also it can't have a negative price. So once you get these numbers, it just becomes a copy-paste game. And it says to 2 decimals, so make sure to copy down to 2 decimals. And you're just basically knowing how to identify your slope and intercept right there. Intercept is first, B0, and then this right here is B1. Make sure to know that this is the quantity of B0, this is the quantity of B1. And we're going over this in a previous problem right here where we were writing out the notation below it, that the predicted value right there, hat means predicted, is equal to the intercept plus the slope times the X variable. Knowing the notation is very important to being able to solve these problems because a lot of times we'll give you notation. Now I want you to predict for 20 terabytes. And when we predict for 20 terabytes, we're just going to go right here and plug in the value for 20 right here. We're just going to take capacity and put 20 right there. And this will give us the Y hat, or predicted price, for a hard drive that has a capacity of 20 terabytes. There we go. And then we're going to subtract. There we go. And that is the predicted price. Boom. Oh, round to the nearest cent. Oh, whoo. Woo. Got to watch that rounding. Could you be able to cover a Chapter 7 quiz? Yeah, which one are you wondering about? Let me know, Marcus. Tell me, and we'll do it. We'll see if we might be able to finish this offer, but let me know which quiz question you're working on, Marcus. You have found the 20 terabyte actually cost this. So this is where you go back to your notation now. And knowing our notation is key right here because we just found the value of Y hat. So that was Y hat, and it says it actually costs this. This is the value of Y. So E equals actual minus predicted. And so we'd go here to the actual cost minus the predicted. And there we go. So the residual equals the actual minus the predicted. And so 2560 minus. So it actually costs more than it was predicted to be. So this is not a good idea to buy it. Because we're above here. We have a positive residual of like $13, which means we're 13 above the predicted price. So, how much would it is paying? No, because the actual price is more than the predicted. Should be right there. Yeah. And once again, how much more or less would you be paying compared to the product? So we found it right here. I rounded a little bit. It says round to the nearest dollar. Really? So we just take 13 anyways. 13 more than expected right there. And does this model over or underestimate the price? So the model is underneath it. The model's the line, and it underestimates. It underestimates right there. This is a really great problem. Oh my gosh. The correlation is very high. Does this mean the model is accurate? No. And they give you the scatter plot. The reason is we've got an extreme point. Basically, the extreme isn't an outlier. Kind of. I take issue with the last part of that question with the way it's worded. I hate that it doesn't show me it anymore. But the last point right there follows the model pretty well, but it's an extreme point, at least in terms of X and Y. Does it have high leverage? Can I get a leverage plot right here? I think it should be down here. We should have that. There's no leverage plot? Do you have to do fit model? So let's predict the price from capacity. This gives you a little more extra information. There's the leverage plot. Yeah, it does have high leverage. And where's the influence plot? Influence plot? Yeah, we don't have to do this. So many things. Cooksty, there it is. Influence. Oh, now we got that saved to the data set, I think. There it is. Ooh, yeah, that point has crazy influence. Yeah, of course. Yeah, because it's got ridiculous leverage. Yeah, that point has way too much influence. You don't have to know Cook's D influence, but that point right there, really way too much influence on the model. And yeah, that'd be a big, big problem for us. So overall, this model, yeah, that point, as extreme as it is causing a lot of issues probably and massively creating the model. And so that's what they're getting out at the end. The New York City data, just want to make sure I'm not missing anything. Yeah, let's go check it out right here. Let's go check out the New York City data. The New York City data. Okay. Okay, New York City data. There's disk drives again. We do a lot of the ones on homework. Which one? Which one right there? Mazzy, which one? If you tell me the number, that'd be great too. The number. Let me know the number. I like that one a lot. It's gonna be the last one, isn't it? Number 2. The New York City Data Initiative reports annual water consumption. The accompanying table shows daily water consumption per capita in gallons from the years given below, along with the scatter plot. A regression to predict daily water consumption per capita from year has an R squared of this. That's the percent of variation Y explained by the variation in X. Complete parts A through C. What are the variables? So it just wants the X and the Y right here, year and daily water consumption. So it's going to be water consumption volume. What are the variables in units? No, it's not R squared. Water consumption in gallons. Population. Daily water consumption, millions gallons per capita. Yeah, and then it should be... Yeah, that's the most accurate right there. What are the units of the slope? I got this one wrong one time, so I can't get it wrong again. Can't do that. It's going to be for each one difference in year, we expect millions of gallons to increase by this. So it's going to be years per millions of gallons per person. Such a weird way of phrasing it. Yeah, millions of gallons per person per year. So it's like each additional year, we expect the millions of gallons to change by this amount. That sounds most accurate. The way they phrase it is just weird because we should be saying like, for each additional year, we expect the millions of gallons of water consumption to increase or decrease by this amount. Yeah, it's such a weird way of phrasing it. What's the correlation right here? So if you look, it's actually going down. Now, so we are given R squared. So how are we going to find R from R squared? And this is where a lot of people usually make the mistake. How are we going to get R from R squared? So be very careful. This is something I went over in class a lot. It's a very common mistake. Square root it. So is the answer. Now be careful. Let's take it and square root it because that's R is correlation. It says what is correlation? And so is this correlation right now? Is that the correlation? But it's negative exactly because correlation indicates direction. Because if you square that, you'll get R squared again. So R squared is correlation squared. Does that make sense, Mozzie, right there? We don't have to usually find R squared by hand. There are ways to find it by hand. It's the reduction of the sums of squared error. We went over it a little bit on the homework. We won't ever really find it by hand. The quickest way we have to find R squared is to do what? Correlation squared. So if you took this value and squared it, you would get R squared. But when you square root it, you have to acknowledge the direction of it. Because square rooting something, it could be positive or negative. But when you look at the graph right here, you can see clearly that it's negative. So when we go from R squared to R, you have to think, does it go up or down? Does that make sense right there? So the direction of this is negative. So when you square root the R squared right there, it becomes a negative correlation because you can see it. You'd have to check it visually or, compute it. So what number did you just square? Correlation R. So R is correlation. So right here, correlation is R. So if you know, and it says to 3 decimals, if yep, so correlation in notation is R. In the back of your notebook, write down all the notation we have. R is equal to correlation, and then R squared is correlation squared. Now, it's not interpreted like correlation, though, but does that make sense, Mousy, right there? That R is correlation. If you square it, you get R squared. So that's really good right there. Do we get it all? Woo! Good question. The last question is the best part of this. Like, there's some parts of my Pearson that are like super awesome, some that are so-so. So the last part is really a really good check to see if you understand going from R squared to R and what we could do with R right there. So really good stuff. Question number 2. Actually, oh, this one. What does it say? So this one right here says, the manager of bookstore. The manager of bookstore. Stat 201. The manager of a bookstore. Okay, let's take a look. The manager of a bookstore. So they're giving us data here to start, and they want to predict their sales from the people working. So we're going to have to bring this over to R, or we don't have to, or jump, I was going to say, because they already give us R right here. So how are we going to get R squared? So how would we get R squared right here? So R is correlation. This is the mean of X. That's the mean of Y, which is the average amount of people we have working. This is the average amount of sales. That's the variation, standard deviation of people working. And that's the variation in sales. So how are we going to take R and turn it into R squared? It's just like it sounds, where you take R and turn it into R squared. So there is the R squared right there. And that is going to be the percent of variation in our sales explained by the amount of people we have working. So remember, R squared is 97% of the variation in our sales is explained by the variation in people working. Usually you take R squared and times it by 100 to turn it into a percentage. So it's right at 97%. I don't think there's any decimals, so it is 97. Let's find out which answer works the best. Which is the percent of variation in number of sales workers? No, we want to look at the variation in sales, which is the percent of variation in sales that can be accounted for by the regression on sales. We regress Y on X. This is where I sometimes get this one wrong. I don't love their interpretations on this. The first part's great. Which is percent of variation in sales that can be accounted for regressing number of salespeople on working on sales. No, it should be this one. The last part of this is regressing Y on X. So regressing sales, which is sales is Y, on number of people working, which is X. So that is it right here. Just a little bit weird. When we do a regression, and I'll tell you how I would interpret this, but when we do a regression, we talk about you could say you regress the X variable right here, which is going to be explaining the number. We use number of people working to explain our sales. So Y is regressed on X, and then this is the plot right here. And then we could fit the line and get the R squared. This one's a little more, would it have accepted 96.9? That's carrying some more decimals for us. That'd be so interesting. Had we done it in jump, would it accept 96.9? I hope it would. It would. So luckily, they're making sure that it works. They've just probably done some rounding in the background. But this right here is a more exact calculation using the data points. And this is a very good regression. So I would say 96.9% of the variation in the sales in thousands of dollars is explained by the amount of people working, or the variation in people working. Blank percent of the variation in Y is explained by the variation in X. And here's what I want to point out to you. On the test, you will need to write out interpretations for the slope, the intercept, and for the R squared. So when you look at my Pearson right here, don't just go straight by their interpretations. Write down your own interpretations. So if you're watching this right now, write down interpretations like 97% of the variation in sales in thousands of dollars is explained by the variation in people working. Blank percent of the variation in Y is explained by the variation in X. Blank percent of the variation in Y is explained by the variation in X. 97% of the variation in sales in thousands of dollars is explained by the variation in people working. The more you get that down, the more you practice it, the more you get to those questions and just answer them easily. Some people get to these questions and they're like, the correlation, and I'm like, no! I'll probably tell my graders to only give like 1 point out of 4 because it's not correlation. We have correlation to talk about correlation. R squared is not correlation. It's the coefficient of determination, which is the percent of variation in y, explained by the variation in x, over the reduction in the sums of squared error from the naive model, but that's a little more technical mathy. Maybe we'll finish up the homework right here. Could do that. Look at all this work in the background. Let's go back and look at that homework right there. Where is that homework? Get the homework done, then we'll do chapter 8 homework during class, maybe. Not like complete class, but hard drive. Yeah, we did the disk drive one. Here's a different disk drive one here. We did the checkout earlier in the video. We'll probably finish this up. Are you asking about, is it this one right here? We just did this one a moment ago, so check that out. It's a little bit of a longer one. We just did this one probably, if you rewind the video, you'll see. You can go down below the video right here and you can rewind live. If it's that one, rewind. Only if it's a different one, because we've got one or two. We got this one right here. You're welcome, Ozzy. Yep. So we'll finish up this right here, homework 1 to 5. And then let's put right here the other one. And if you're stuck, let me know. Okay. Let's say right here. To the right are the residuals. Okay, so showing us how much we miss by. Of the price on capacity for hard drives. Which drive capacity contributes the most to the sums of the minimized squared error? So residuals are errors. Residual is how much you miss by. When you think about a residual, it's how much the point is above or below the line. So that residual right here is negative 0.6516. This is a different problem, but the actual, which is y, where the point is at, minus the predicted, which is the line, is the residual. Residual equals actual minus predicted. And I have it a little color-coded right here, showing you the orange is the line. Line makes predictions, so the line is going to predict the weight. And then you take the actual minus the predicted, and if you look, the actual was 3, the predicted was 3.6516, so it's negative, means it's below the line. This is the biggest, and the reason we square these is because when you square them, they're always positive. So if you sum the squared residuals, you will always get positive numbers. But if you sum the residuals, let's see if they did this properly. Yeah, it looks like they could have. If you just take the residuals and sum them, watch what happens. Let's see if they did this properly. And this is a good concept to know. If you sum the residuals, write this down. Do you know what you'll get? Does anyone know in the chat? I'll throw 100 points. If you sum the residuals, the sum of the residuals is equal to, yeah, they did it pretty well. They didn't carry enough decimals. It's equal to 0. Abigail, good to see you here. But the sum of the residuals is equal to 0 because some points are above the line, some points are below the line. So when you sum the residuals, you get 0. That's why we square them. So it's saying, what does this, okay, so which of these contributes the most? It's the largest one right there. And we just square that, so 17.69. We can make it negative, but when you square it, it's always going to be positive. It says to the nearest integer or a decimal. I think this is what it wants. Wait, what? Which drive, oh, well, I found the sum of the squared error. Which drive capacity? There we go. Be very careful. It wasn't asking for the squared residual, which I thought it wanted. It was just saying which capacity associated with which residual is giving the largest sums of squared error. Be very careful. Which drive capacity contributes most to the sums of the squares and that we are trying to minimize. And this one right here is the one. And it wouldn't matter if it's positive because you're squaring it. A negative residual means that the drive is below what we predicted it to be. So it costs less than what we might have expected. And that's because a negative residual, here's the expected, the line is the expected. So if it's negative, the actual is below. So the drive would cost less than we would expect it from this model. And it's, via its capacity. That sounds right. Negative means the drive costs less than the model would expect for this model and its capacity. A residual of negative 17.11 indicates that the cost yeah, then they're trying to make sure you understand your X and your Y relationships right there. Good. That's pretty good. The ending of that gets a little tricky right there. They're just having you interpret, like we were predicting the weights of a baby right here, and the negative residual right here means that this baby weighs 0.6516 less than we would have expected, because the line is the expected. So the baby weighs less than expected because we're predicting weight of a baby. And so we know that the baby is 48 centimeters. So we used 48 to make the prediction by plugging 48 in right here. And then after we made the prediction, we found that it actually weighs 3 kilograms. So this would be the actual. This was the prediction from the model. We just plugged in 48 to do that. And so the actual minus the predicted is negative, meaning the baby weighed less than it was predicted to weigh. And you can see that the point right here, which is the actual, is below the line. Very important stuff on residuals and understanding how to interpret them. Oh, darn. Well, we already did this one also in the homework. They show you the r squared value anyways, or the r value. To get r squared, it is going to be simply squaring r. So we just take r and we square it to get r squared. This is none. That's going to be 90%. And times by 100 to turn to a percentage. Now, the big thing to know about this is r squared is not correlation. It's the percent of variation in y explained by the variation in x. So write out your interpretations. If you're watching this right now, be able to write out your slope, your intercept, and your r squared interpretations. Go to the notes, go to the homeworks or the quizzes or the lectures where we go over this, and write them down. So I'm going to interpret this value without looking at their interpretations. So we are predicting the sales in thousands of dollars this bookstore will get from the people working. So the interpretation is, without putting in the numbers, blank percent of the variation in y is explained by the variation in x. R squared percent of the variation in y is explained by the variation in x. 90% of the variation in sales of thousands of dollars is explained by the variation in number of people working. So that's the key to doing the questions on the test. Now, with my Pearson, they're going to give you a standard structure that is similar-esque. So, which is the percent of variation in sales that can be accounted for by a regression on sales on number of people working. I think that's the right one here, because they're regressing y on x. So the x is the salespeople working, and regressing y, which is sales on number of people working, regressing y on x. 90% of the variation in sales. We want to understand sales. There we go. Once again, write it down. If our data in a scatter plot is straight enough, we can model our data with a... This is the QQ straight enough. No outliers right here, and it's going to be a line. That is a linear model right there. So if it's straight enough, we can add a line to it. Which conditions should you recheck? Wow, I mean, they just want you to know QQ straight enough, no outliers, plot doesn't thicken. I prefer to say, for outlier condition, I prefer to say no outliers. And let me tell you why I say all the conditions the way I do. QQ means two quantitative variables. You should know it more than QQ, because like, what does QQ mean? Well, QQ means X and Y are both quantitative variables. Straight enough means the line goes through the data well enough. We saw one earlier with the drive and the capacity where it looked to have a bit of a bend. And if you look right here at this, the line is really not going through the center of the data. It's the line starts out below the data, then above the data, and then below the data again. You want the line to cut through the middle of the data, and we don't see it with this model here either. We might see it with one of the first ones I made right here. That line cuts through the middle. You might say this model might have a bit of a problem with plot doesn't thicken because it gets a lot thicker in this area. Or you could say maybe it's a little bit of an outlier issue. So QQ, weight and horsepower of a car are both quantitative. Straight enough, the line goes through the middle of the data. I mean, that's, the points are below it, but it's not the worst. It's doing all right-ish. The ones we saw earlier where there's a bend, where the points bend around the data, are bad. And so that's straight enough mostly. No outliers. Definitely we got a problem over here. That's a bit of an outlier. It's far away from the line, which is the bivariate relationship. And it could also be a symptom of plot thickening. So we either have a little bit of plot thickening because the plot is getting thicker. And when we talk about plot thickening, we're talking about the typical distance points are away from the line. So if you look, the strength should be relatively constant throughout the model. There's one area right there that either has outliers or an issue of plot thickening, where we would say maybe the conditions are not satisfied. So you have to check two quantitative variables. Does the straight line go through the model? Are there no outliers? And is there not plot thickening? So I like to say QQ straight enough, no outliers, plot doesn't thicken. And I say it that way because I want to say the positive ideas like Outliers to me means no outliers. That's a good thing. Does the plot thicken? I prefer to say plot doesn't thicken because that's a good thing. So those are the good ways of saying those conditions. And that's the full homework. We've now just done chapter 7 homework, 6 to 9. Woo! Full homework done. What other questions are there? Might take a little bit of a break here. Got the full homework done. Start the homeworks early. Ask questions. Let me know. We'll see what people are saying. Someone give a thumbs up like that. We have 7 boosts on Discord. That's pretty crazy. Next week is spring break, and I can't believe it already. Hey, Jesse, what's up? Might head off here in a moment, but do you have questions, Jesse? What are you wondering about? We just did the whole homework 7, and we did a little bit of quiz 7. So maybe we'll do some quiz during class. I talked about doing homework or quizzes during class, and yeah. A few more classes, then we're done for the for spring break coming up. Spring break, holy mackerel! It's gonna be a good week off. Yeah, we should do quizzes during class, right, Mazzy? So Maisie, right? Maisie. I think we should do quizzes during class. Bed Bath & Beyond wants to get a hold of me. Then we could do questions we haven't done. And we're going to do chapters 7 and 8 today in class. And so my goal is you understand regression after today. Maisie. I'll throw some points out here. But overall, good work. I get called everything. It's okay. Same here. I get a lot of interesting. It's weird. You grow up with your name and then you get a lot of interesting variants on it. So you would think I wouldn't, but yeah, everyone does, I guess. Some people more than others. So, well, with that, I think we'll take a little break here until class. Till then, I'll see everyone soon. Bye for now, everyone. Bye.